In our last class, we introduced a new electronic component, the operational amplifier or Opamp, that is going to greatly increase the number of interesting circuits that we can build in electrical engineering. We saw that an Opamp was basically a voltage-controlled voltage source, which took the difference between two input terminals, the non-inverting terminal and the inverting terminal, and amplified that by a very large amount, A, to give us the output voltage. So V out was nothing more than A times V plus minus V minus. When we talked about the Opamp, we then saw that using the Opamp in open loop mode is something that we typically do not do. Instead, we connect external resistors, capacitors, and other components to the Opamp and use it in what's called closed loop mode. We then saw that to try to solve Opamp circuits, you had to use a model for the Opamp. So we started with something called the standard behavioral model. Basically, this used the fact that the Opamp is nothing more than a voltage-controlled voltage source. It took into account two additional things: a very large internal resistance called Rn at the input and a very small internal resistance at the output called Rout. Unfortunately, we saw that even for a very simple Opamp circuit, when you use the standard behavioral model, the analysis is going to be very difficult. So this is a very hard model to use. Fortunately, we saw at the end of last lecture that if you make a couple assumptions, you can get a much simpler model. And this is going to be the idealized model of the Opamp that we're going to talk about in more detail today. The assumptions we're making are as follows. First off, the gain of the Opamp is very, very large, 10 to the 5th, 10 to the 6th, 10 to the 7th. We're going to assume in the idealized model, it's infinity. Second assumption, this input resistance Rn that is very, very large, we're going to assume that it's infinity. By assuming it's infinity, basically we're saying there's now an open circuit between the inverting and non-inverting terminals. If there's an open circuit between those terminals, what does that mean about the current going into the inverting and the non-inverting terminals? The current going into the terminals both have to be zero if Rn is infinity. So that is the next assumption with the idealized model. In reality, there's going to be a very small current going into these terminals because they are connected to each other. If you think back to the actual circuit for the Opamp, you see that there are connections between the inverting and the non-inverting terminals. So there is going to be a current. However, in our idealized model, by assuming that Rn is infinity, that current is going to be zero. The final assumption we're going to make in the idealized model is that this output resistance, which in practice is a small number, is going to be so small that we're going to make it zero. If we assume that Rout is zero, the voltage across the terminals of the voltage-controlled voltage source would be the same as the voltage available external to the Opamp. What we're going to see now is using this idealized model instead of the standard behavioral model for the Opamp is going to make it much easier to solve Opamp circuits. So we're going to see that this is an easy model to use. So we're going to spend the rest of the lecture today to talk more about the idealized Opamp model and start using the idealized model to solve Opamp circuits. What we're going to see is that there are two assumptions we can make in solving Opamp circuits provided the two key conditions are met. The first condition is that the Opamp circuit has to be a closed loop negative feedback circuit. So it has to be closed loop and it has to involve negative feedback. This is how the vast majority of Opamp circuits are going to be. So this restriction is simple to meet. The second one is we have to use this idealized Opamp model that we introduced at the end of last class. With these two assumptions in place, we now have two simplifications that are going to make it easy to come up with an algorithm. The first of these is what we call the virtual short circuit approximation, or VSCA. What we're going to see here is that the feedback between the output of the Opamp and the inverting terminal of the Opamp causes the voltage at the inverting terminal to basically equal the voltage at the non-inverting terminal. In other words, V minus is going to be approximately equal to V plus. So in the real world, they're approximately equal to each other. In this ideal case, we're going to say they're equal to each other. We're saying there's a virtual short circuit between the terminals. We're not saying that the inverting and the non-inverting terminals are connected. What we are saying is whatever voltage we're going to get at the non-inverting terminal, the voltage at the inverting terminal will be virtually the same thing. and we'll give an argument for that on the next page. The second assumption is what we call the zero input current approximation. On the previous page, we argued that if Rin is very, very large, the currents into the inverting and non-inverting terminals of the op-amp are going to be very, very small. And in the ideal case where Rin is infinity, I minus and I plus, which are the currents into the inverting and non-inverting terminals of the op-amp respectively, are both going to be 0. So we're going to use these two approximations to make our algorithm for solving op-amp circuits much simpler. The zero input current approximation is pretty easy to understand. It's pretty clear to see that if Rin is very, very large, the current flowing into those terminals will be quite small. The second argument, this virtual short circuit approximation, is a little bit tougher to understand. So let's try to come up with an intuitive argument for that. We know that the output voltage of the op-amp is going to be a huge magnification of the difference between the voltage at the non-inverting and inverting input terminals. Because A is extremely large, the only way to get a reasonable output voltage is to require that the difference between the two input voltages is almost 0. So in other words, if you're going to have an output voltage of 5 volts, 10 volts, 7 volts, the difference between V plus and V minus needs to be so small that we're going to make it approximately 0. So what's going to happen in these circuits is the negative feedback is going to cause the op-amp to try to attain and stay at some equilibrium. So for example, you might have the voltage at the non-inverting terminal at some fixed value. This example, it's at ground. What's going to happen because of the negative feedback is the voltage at this terminal will self-adjust to try to reach an equilibrium value. And that is due to the negative feedback. So let me try to explain how that happens here. So let's assume that you have some equilibrium where this voltage at the non-inverting terminal and this voltage at the inverting terminal are close to each other. So you have some input voltage and you have those things close to each other. What happens if you do a slight increase to the input voltage? So a slight increase to the input voltage is going to cause what? It's going to cause a slight increase to the inverting terminal's voltage. But what is that going to do? If you increase the voltage at the inverting terminal, the output, which is A times V plus minus V minus, is going to go down a little bit. And what's going to happen is this slight rise here is going to be countered by this drop here, and we're going to see that V minus is going to stay close to V plus. If you can't quite grasp this, do not worry about it. It's not critically important for working with op-amps. I also think that as you work with op-amps, you'll find that this becomes more clear as you go through some examples. At this point, let's develop the algorithm and get to a couple examples because that will really help illustrate what's going on here. So how do you solve op-amp circuits when you use the idealized model? First thing I need to point out here is this algorithm only works for op-amp circuits that have negative feedback and that are operating in the linear region. The reason that these two requirements are necessary is because they have to be present for these two assumptions here, the virtual short circuit approximation and the zero input current approximation, to be valid. So what are the steps? The first step is you do want to verify negative feedback. Once again, this algorithm only works when you have the output of the op-amp fed through some circuit components back to the inverting terminal of the op-amp. The next step is to use some circuit analysis technique to determine the voltage at the non-inverting terminal. Remember when doing this that we're going to assume that the current into that terminal is 0, so that typically makes this analysis pretty simple. The third step is we're going to invoke the virtual short circuit approximation rule and set V minus equal to V plus. Whatever we determine V plus has to be, V minus we're going to set equal to the same thing. In reality, V minus is not going to be quite the same thing, but it's going to be very, very, very close. For example, if V plus was 2 volts, V minus might be 1.9995 volts. But for the sake of this algorithm, we're going to set V minus equal to V plus. The argument, once again, the only way the output can be at a reasonable voltage level is if those two inputs are so close to each other that they're virtually the same. That's the virtual short circuit approximation rule. The next step is the key step in this algorithm. We write a KCL equation at the inverting terminal. Once again, Just like when we solve for the voltage at the non-inverting terminal, when we solve for the voltage at the inverting terminal, remember that the current into that terminal itself is going to be 0. Once you do step 4, the rest of the steps are pretty simple. If necessary, you might write additional KCL equations, but one equation you do not write, at least at this point, you do not write a KCL equation at the output terminal of the op-amp. The next step is a little bit of algebra to get your equation in the form that you want. Finally, at the very end, if you need to find the current leaving the op-amp, you can apply KCL at the output terminal. You do this only after the voltage is known. So you do not write KCL equations at the output terminal when you're solving for the output voltage, but once you know the output voltage, you could do a KCL equation at that output terminal to find current. And we'll see that in some examples. This algorithm seems a little complicated. Don't worry about it. You're going to see on the next page how absolutely simple it is. Let's go back to the inverting amplifier example we did last class. So an inverting amplifier, you basically have a resistor R1 connected between the input signal and the inverting terminal of the op-amp, and another resistor R2 connected between the inverting terminal of the op-amp and the output terminal of the op-amp. And we saw that if you replaced the op-amp by its standard behavioral model, we got an absolutely horrendous equation for the gain. We then saw that by making these simplifications, that the math gets a little simpler and you get a much easier final answer. What we're going to see now is that you can get to this final answer doing hardly any work at all. So even with these simplifications, there was still a lot of work here to get to this final point. What we're going to see now is using the idealized op-amp algorithm, you can get to this answer in very few steps. So here we have this inverting amplifier circuit again, and we're now going to revisit it using the ideal op-amp algorithm from the previous page. So the first thing you want to do is check to make sure you have negative feedback. Do you have negative feedback? Yes. We have a resistor, R2, feeding back between the output of the op-amp and the inverting input terminal of the op-amp. That means that we can use this idealized op-amp model to solve the circuit. Next thing we do then is we solve for the voltage at the non-inverting terminal. It's trivial in this problem. The non-inverting terminal is connected to ground, so V plus is equal to 0 volts. The next step is to set V minus equal to V plus. The virtual short circuit approximation says that the voltage at the inverting terminal is going to be very, very close to the voltage at the non-inverting terminal. In this case, 0 volts. In the real circuit, does V minus equal 0 volts? No. It might be slightly less or slightly larger than that, but they're going to be so close that for all intents and purposes, we say that they are the same. The next step then, which is the only real step in this algorithm, is to do KCL at the inverting input terminal. Basically, we're saying that this current plus that current plus that current equals 0. So if you do KCL at the V minus node, what do you get? The current to the left is going to be V minus minus Vin. Vin is whatever this input signal is here, over R1. So we get 0 minus Vin over R1. Current to the right is a current into the inverting terminal of the op-amp. That's 0. That's because we're assuming that I minus is equal to 0. That's one of our assumptions. Third is the current going up. That's going to be 0 volts minus V out over R2. So we get 0 minus V out over R2. The sum of those three currents is equal to 0. Now we play around with this equation, write V out as a function of V in. So bringing this to the other side and multiplying everything by R2, we get our final answer that V out is equal to negative R2 over R1 times V in. Same result we got a few pages earlier in our previous lecture with much, much less work. We had one relatively simple KCL equation to write. the fact that we use the virtual short circuit approximation, this voltage equals this voltage, and we use the fact that the current into the two terminals, this current here and this current here, are both 0, allows us to get this answer without much work at all. A couple things to note about this equation. First off, note that the gain is negative. The gain is this term here. This is the gain, and it's a closed loop gain, so we call it G. So the first thing we note is the closed loop gain G is negative. This is why this is called an inverting amplifier. It inverts the input signal. So for example, if the input signal looks something like this, the output signal would be an amplified version of it, but it would be inverted. So when the input was negative, the output was positive, and vice versa. So that's what we mean by a negative gain or an inverting amplifier. Second thing we see is that the gain magnitude can be greater than 1 or less than 1. So we call it an inverting amplifier. An amplifier sort of implies that the output voltage is going to be larger than the input voltage, but there's nothing magical about that. If we make R2 less than R1, we can get the output voltage to have a smaller amplitude than the input voltage. So the gain magnitude can be greater than 1 or it can be less than 1. The third thing that we see is that this equation is independent of the op-amp's open loop gain A. And this is what we want. Remember in the last class we talked about how A can vary from op-amp to op-amp, or even within a particular op-amp depending upon the temperature or depending upon the frequency of the input signal. So having an output voltage that doesn't really depend upon A, as long as A is really, really large, is a good thing to have. But now that we've developed this input-output relationship for an inverting amplifier without doing much work at all, we can now answer a couple more questions about this. The first question is, what effect would a resistor placed between the V plus terminal and ground have? So in other words, if we were to place a resistor here, would it have any effect on this answer? Well, what do you know about the current into the non-inverting terminal of the op-amp? You know that this current is 0, which means that that resistor is not going to have a voltage drop across it regardless, which means the voltage at this terminal here is going to be 0 volts even with the resistor there. So ideally, it has no effect. Why does it have no effect? Because the current into the non-inverting terminal of the op-amp is 0. So V plus is going to be 0 volts regardless of having a resistor between the non-inverting terminal and ground. So the next question is, what effect would a resistor placed between the inverting terminal and ground have? So in other words, if we put a resistor here, what effect would that have? If you look back to this equation here, when you write the sum of the currents leaving that inverting terminal, you'd have an additional current flowing through here. But what is that current? The voltage at this point is 0. The voltage at this point, because it's connected to ground, is 0. You get 0 minus 0. So regardless of what that resistor would be, that current would be 0. So the equation for the output voltage would be unaffected. So once again, ideally, it would also have no effect. Why would this have no effect? Because the voltage at the inverting input terminal is already virtually 0 volts, so there would be virtually no current flowing through that added resistor. The final question is, what effect would a resistor placed between the output terminal and ground have? So in other words, if we were to connect up a load, let's call this RL, connected between V out and ground, what effect would this have on this equation? Well, once again, think back to this KCL equation here. Does the current through this component here show up at all in this equation? It does not. So what we see is that a resistor placed between V out and ground would have no effect on the voltage at V out. This is a very important result that we're going to see time and time again with op-amps. So in an ideal situation, a load resistance has no effect on V out, which is sort of a surprising result. Now you have to be careful here. We cannot say that the load resistor has no effect on the circuit because it does affect the current coming out of the op-amp. This is a current leaving the op-amp. That would change if we added a load resistor here. And we'll see this as we do some examples later on. What this means, this is also later, is that the power delivered by the op-amp is affected. So it does affect the current leaving the op-amp and it affects the op-amp's power, but it does not affect the voltage at the output. So what we saw here in these three questions is a resistor here will not change V out, a resistor added here will not change V out, and a resistor added here will not change V out. And this is all due to the ideal properties of the op-amp. Let's do a couple simple examples here. So we're asked to design an op-amp circuit where the output voltage is negative 25 times the input voltage. In other words, we're going to design a circuit that amplifies an input signal by a factor of negative 25. So the fact we want a negative gain right away signifies that we want an op-amp in an inverting amplifier configuration. So you have the op-amp here. You have to ground the non-inverting terminal. Then you have a feedback resistor between the inverting terminal and the output of the op-amp, and that output voltage is measured versus ground. And then you have another resistor between the inverting terminal and your input signal. We'll call it Vin of t. The only requirement is that the ratio of this resistance over this resistance has to be 25. Specifically, so we want R2 over R1 to be 25. What you see here is you have an infinite number of solutions. One value that would work would be 25 kiloohms here and 1 kiloohm here. But once again, that's not unique. 50 kiloohms and 2 kiloohms works. 100 kiloohms and 4 kiloohms works, etc. So one question you might ask is, what value of resistors should you use here? Typically, you want these external resistors to be in the tens of ohms to maybe a mega ohm range. So one thing I want to do here is to show that even though we're using an ideal model here, the value you get for gain, negative 25, is very close to what you'd get actually. So if you go back once again a few pages, we had this horrendous expression for the gain using the standard behavioral model, where we do take R in and R out and A into account. In the ideal model, we don't take them into account. A is infinity, R out is 0, R in is infinity. But in the standard behavioral model, you take those into account. So let's do a calculation here and see what the actual gain would be if you use the standard behavioral model. Well, let's assume that A was 10 to the 5th, and let's assume that R in is 1 mega ohm, large but not infinity, and let's assume that R out was 50 ohms, small but not 0. If you plug those values plus our value for R2 and R1, 25 kiloohm and 1 kiloohm, into that gain equation, you get a closed loop gain of minus 24.9935. So what we see using this ideal model, which is developed very simply with one KCL equation, we get an answer that's very close to what the true gain would be anyway. So this validates the use of this idealized model. It's not as exact as a standard behavioral model, but it's so much less work that it's worth doing. So this works because A is very large, R in is very large, and R out is quite small. But we're going to see that even if you change these each by a factor of 10, the ideal model is still going to be a close approximation of what really happens. So let's assume that A is only 10 to the 4th, not 10 to the 5th. So it's even further from infinity. Let's assume that R in is not 1 mega ohm, but 100 kiloohms. So once again, it's further from the ideal situation. And let's assume that R out is not 50 ohms, but 500 ohms. Once again, further from the ideal situation. So you would expect here that the actual gain would be further from the idealized gain of 25. Sure enough, if you plug this into that very long equation, you get a closed loop gain of minus 24.9332. Once again, we see here that the ideal model gives us an answer very, very close to the real answer using the standard behavioral model. What this shows once again is that this ideal model works, and because it makes the math so much simpler, it's a worthwhile trade-off. So let's do one more quick example on this page here. In this example, we're asked to design an op-amp circuit that gives a value of negative 5 volts at the output when the input is 15 volts. So in other words, in this example, we want the closed loop gain to be negative 5/15 or negative 1/3. Because we're inverting the signal, we want to have an inverting amplifier, so the non-inverting terminal is grounded. The inverting terminal is connected through a resistor, a feedback resistor, to the output. And then another resistor is connected between the inverting terminal and the input signal, which in this case we're told what it is. We're told that it is a 15 volt source. This is going to be R2, that's going to be R1. Now, to get a V out of 5 volts, we want a gain of negative 1/3, which means the ratio of R2 to R1 has to be 1/3. So just like in the previous example, there's an infinite number of solutions, but we're going to pick resistor values sort of in a mid-range. We're going to pick 10 kiloohms here and 30 kiloohms here. What is important is to remember, for this ideal model to be very close to the real value, you want those resistors to be much less than this internal input resistance here, and you want it to be much larger than this internal output resistance here. Remember, the internal output resistance is very small and the internal input resistance is very large. As long as these two external resistors are large compared to this resistor and small compared to this resistor, we're okay. So 10K and 30K works fine. 100K and 300K would work fine. If you choose external resistors in the tens of ohms to the 1 mega ohm range, you're typically going to be okay with this ideal model. So far, we've only looked at one canonical amplifier form for closed-loop operational amplifier circuits, and that is the inverting amplifier. We are going to soon look at other types of amplifier circuits. Before we do that, however, there are two more topics we need to cover. One is op-amp power, the other one is op-amp saturation. Op-amp power is similar to power associated with any other device. It is the voltage across the element times the current through the element. Specifically for an op-amp, the power delivered by the op-amp is the product of the voltage at the output terminal and the current leaving the output terminal. Key terms here, we're talking about the power delivered, and we measure the current leaving. So what do we mean by the current leaving the op-amp? When you connect an op-amp up to a circuit, the current coming out of the op-amp terminal is the current leaving, and we're going to call that I out. So the power associated with the op-amp, and I should point out here this is a delivered power, is the output voltage V out times this current coming out of the op-amp. The way you find this output current is by doing a KCL equation at the V out terminal once the voltage is determined. As I said before, you never do a KCL equation at the output terminal of an op-amp when you're trying to find the output voltage. But once you know that voltage, we're going to see that you can then do KCL to find the output current and therefore the power associated with the op-amp. The power coming from the op-amp is not created magically. It's ultimately coming from the power supplies connected up to the op-amp. So remember, an op-amp has a VCC and a VEE connection powering the op-amp, plus or minus 15 volts, plus or minus 5 volts, whatever. So ultimately, it is that power supply that's providing the energy and the power to go through the op-amp and ultimately to drive the circuit. Final comment about power before we do an example is there is a limit to how much current an op-amp can produce, and that's going to be a function of the op-amp itself. So because there's a limit to the current the op-amp can produce, and there's a limit to the voltage at the output of the op-amp because of the power supplies, there's going to be a limit to the power that the op-amp can provide. As far as this current limit for the LF412, which is the op amp that we're going to be using in our lab, I out is typically limited to be less than 20 or 30 milliamp. There are some op amp chips that are able to produce much higher currents, and we typically call them power op amps or power amplifiers. And they are used, for example, to drive audio equipment where you need more current. But for the LF412 that we use in our lab, the limit once again is about 20 to 30 milliamps. So let's do an example to illustrate some of these power-related concepts. So here we have an inverting amplifier circuit, but unlike the examples before, notice we have a load resistor attached to the output of the op amp. We're asked to find V out and verify that the output voltage is independent of this load resistance. We're going to see that that 10 kilo ohm load resistor does not show up anywhere in the equations to determine V out. Once we find the voltage V out, we're going to find the power supplied by the op amp by first finding this current I out coming out of the op amp and then using the power equation. And we're going to see that the power associated with the op amp does depend upon that load resistance. So let's solve this circuit. Once again, this is an inverting amplifier. So the way you analyze it, you first find the voltage at the non-inverting terminal. We get that from inspection. It's 0 volts. And because of the virtual short circuit approximation, the voltage at the inverting terminal is also 0 volts. The next step is we do KCL at the inverting input terminal. Basically, we're summing that current plus that current plus that current equals 0. So KCL at the V minus node, the current to the left is going to be 0 minus 1 volt over 1 kilo ohm. The current going to the right, the current into the inverting terminal, is 0 amps. Once again, remember, I minus is 0. And the current going up is 0 volts minus V out, that's what we're solving for, over 10 kilo ohms. The sum of those three currents is equal to 0. You solve for V out, we get that V out is equal to minus 10 volts. Notice, nowhere in this equation here did this value come into play. The 10K that is in this equation is this 10 kilo ohm resistor here, not the load resistance. So notice, even if that load resistance was 20 kilo ohms or 5 kilo ohms or 100 kilo ohms, it would not have changed this equation, so it would not change V out. So we showed that the output voltage V out is independent of that load resistance RL. One other thing I want to point out here is we did not even have to do this KCL equation. We know that it is an inverting op amp circuit. We know that the closed loop gain is minus R2 over R1. So just looking at the circuit, we see that the gain is minus 10 over 1 or minus 10. So if the input is 1 volt, the output would have to be negative 10 volts. Nevertheless, even though you could memorize these equations such as minus R2 over R1, it's probably good to get in the habit of writing the KCL equations because there might be some circuits that don't fall into some of these canonical forms. So at this point, we solved the first part of this problem. We found V out. Now what we need to do is find the power supplied by the op amp and verify that it does depend on the load resistance. So we'll do that now. So to find the power, we first need to find I out. How do you find I out? You do KCL at the V out node. Remember, you never do KCL at the V out node when finding the voltage V out, but now that you know V out, we could do KCL to find the current. So basically, we're doing a KCL equation here. We know that this current plus this current plus this current has to equal 0. So let's do that math. Current to the left is negative I out. Current going down is what? It's V out minus 0 over RL. The current going up is what? V out minus 0 volts over 10 kilo ohms. The sum of those three currents has to equal 0. But what do we know? We know that V out is negative 10 volts. We also know that RL is 10 kilo ohms. We're given that. So we can now solve for I out, and we get I out is equal to negative 0.002 amps, or negative 2 milliamps. An important thing to point out here, An op-amp is always going to deliver power, so the product of V out times I out is always going to be positive. What you're going to see is that if V out is negative, I out is going to be negative. In other words, the current will go into the op-amp if the output voltage is negative. If the output voltage is positive, the current is always going to come out of the op-amp. Either way, we're always going to get a supplied power for the op-amp. So the power supplied here is what? The supplied power, using the power equation for the op-amp, is the voltage at the output, negative 10 volts, times the current coming out of the op-amp, which is minus 0.002 amps. You work out the math, it's 20 milliwatts. The important thing here is because of this resistor here, this load resistance here, we see that as RL goes down, as the load resistance gets smaller, the magnitude of the current leaving the op-amp is going to go up, and so the power supplied by the op-amp is going to go up. But it cannot go up forever. Eventually what's going to happen, if RL is too small, I out hits the limit of the op-amp and it stops operating the way it's supposed to. We call this situation current saturation. Current saturation is not to be confused with voltage saturation that we looked at briefly at the beginning of this packet of notes and we'll look at again on the next slide, but they both are related to the limitations of the op-amp. An op-amp can only produce a certain voltage based upon the power supplies that are powering the op-amp. Likewise, the op-amp can only produce a certain current based upon the make and model of the op-amp and how it's designed. So let's talk about saturation now. Specifically, we're talking about closed loop saturation. We talked about open loop saturation when we first talked about the input-output relationship of the op-amp. We saw that an op-amp powered by, let's say, plus or minus 15 volts can never produce more than 15 volts at the output terminals. That was what we called voltage saturation. That existed for open loop mode, but it also exists in closed loop mode. Where saturation is important in a closed loop configuration is remembering that the virtual short circuit approximation and the input-output relationships for a closed loop amplifier are valid only as long as the op-amp is operating in its linear region. In other words, once it hits saturation, you can no longer use the virtual short circuit approximation as we're going to see in an example soon. So what happens when we hit saturation? We call that clipping. So here's an example here. Suppose you have a closed loop amplifier with a gain equal to -5. Suppose you have an input with the maximum voltage of 2 volts. It's going to get amplified by -5, so it's going to have a maximum output voltage of plus or minus 10 volts. If this is powered by plus or minus 15 volt source, this is well within the limits, and so the output looks like a amplified version of the input. What happens, however, if you take the same op-amp powered by the same plus or minus 15 volt source, but now drive it with an input that has a magnitude of 4 volts? The gain is still -5, so now it wants to have an amplitude of 4 times 5 or 20 volts. So it would want to go all the way up to, let's say, there and down to there to -20, once again positive 20, -20. It would want to hit 20 volts. But what happens, the op-amp is limited because of the power supply voltage, and so it sort of levels off right at the saturation voltage, Vsat, which is going to be close to the power supply voltage. Remember, the saturation voltages are typically close to the power supply voltages. Anyway, this situation here is what we call clipping. It's called clipping because the top part of the waveform is sort of clipped off the circuit. Clipping is usually a very bad thing. It gives distortion. If it's music, for example, it's going to sound bad. If it's other types of signals, it's going to give you some wrong data, whatnot. So clipping is typically something you want to avoid. So saturation is something you want to avoid. So we see from this illustration here that to avoid saturation or clipping, they mean the same thing. There are going to be limits on the amplitude of the input signal. And what are those limits? Well, they're going to be related to two things: the gain of the amplifier and the value of the saturation voltage. So let's look at those equations. So when you have a standard inverting amplifier, you have a straight line of slope G, which is equal to what? Negative R2 over R1. So this slope is the gain of the amplifier, which is negative R2 over R1. So how do we relate the gain to the input voltage and the saturation voltage? Well, what we see is that once we hit the saturation voltage, we're no longer going to have that linear increase in the output voltage. It's going to level off at plus or minus saturation. So what we see is when we're operating in this part of the op-amp, we call this the linear region, the output is what? It's just negative R2 over R1 times V in. What happens if the input is in this region or this region, it's too large, so when you multiply it by the gain G, you hit the saturation voltage and you get your clipping. The term V linear is sort of the boundary of where the input signal needs to be to avoid saturation. So what is V linear? V linear is the value of the input signal that causes the output to hit saturation. So when the input is V linear, it gets multiplied by G to give us plus or minus V sat. So if you make an equation out of that, you see that V linear times the absolute value of the gain equals the saturation voltage. We can then solve for V linear and we get this expression here. V linear is the saturation voltage divided by the absolute value of the gain, which for an inverting amplifier is what? Negative R2 over R1 is the gain, so the absolute value of that is R2 over R1, and we get this expression here. When we talked about op-amps in open loop mode, there was also a linear region. The difference there is in the open loop mode, the linear region was what? The saturation voltage divided by open loop gain A. Remember, open loop gain A is gigantic, so the linear region for an op-amp in open loop mode is going to be very narrow, whereas in a closed loop configuration, because the gain slope is much less than in the open loop situation, you have a much wider linear region here. So let's look at an example. Question here is at what value of V in does this op-amp enter saturation? We notice from inspection that this is an inverting amplifier. The non-inverting input terminal is connected to ground. You have a resistor feeding back between the output and the inverting input terminal and another resistor going to a voltage source. We could use the algorithm to find V out, but we really don't even need to do that here because we've recognized the fact that this is an inverting amplifier. So what do we know? The gain is equal to minus R2 over R1. So the gain is minus 5. You could get that, of course, by doing a KCL equation here, but we don't need to do that because we recognize that this is an inverting amplifier. We're also told in this particular problem that saturation voltage is plus or minus 14 volts. Where does this come from? Well, we're just told it, but what we can probably imagine is that this is being powered by plus 15 volts and minus 15 volts, and there's a 1 volt headroom. Remember, headroom is the difference between the saturation voltage and the power supply voltage. Anyway, knowing that the saturation voltage is 14 and knowing that the gain is negative 5, we can determine the linear range. From the previous page, V linear is V saturation over R2 over R1. So V linear in this case is 14 volts over R2 over R1 is 5, or 14/5 of a volt. Let's plot this on an input-output plot. So our x-axis is V in, the input voltage. The y-axis is the output voltage, V out. We know because this is an inverting amplifier, it's going to have a slope equal to the gain. In this case, it is minus 5. But that does not continue on forever because once your output voltage hits saturation, which is either plus 14 volts or minus 14 volts, it cannot increase anymore. And so the figure looks something like this and this. To determine the linear region then, we basically have to find what input gives us the minus 14 volt saturation or the plus 14 volt saturation, and we saw in the math above that it was plus and minus 14/5 of a volt. So the linear region for this circuit would be plus or minus 14/5 of a volt. If the input is within this range, the op-amp is operating as you expect it to, and it gives us a voltage equal to -5 times the input voltage. If, on the other hand, the input is operating outside this range, you don't get the result that you expect, and we call that the saturation region. So we have saturation region, there and there, and we have the linear region in the middle here. For the most part, as I said before, we always want to operate op-amp circuits when they're in the linear region, because this is the only region where the virtual short circuit approximation holds. We're going to see next class that if you're outside the linear region of operation, the voltage at the inverting terminal no longer equals the voltage at the non-inverting terminal. You lose the virtual short circuit approximation, and you have to analyze op-amp circuits slightly differently. So this is a good place to stop for now. We'll pick this up in next class, and we'll look to see how you can analyze op-amp circuits in saturation. Have a good day.